All right, so this is just going to be a couple of questions from chapter 11. And then with each of them, I'm going to have the question up there just for a little bit. Um, but then if you want to work on them on your own, just pause the video so you have time to kind of go through it because I'm just going to start going through the solutions for each of them pretty quickly after putting up the first slide. With these ones, we want to first determine for each of these pairs which is going to have the highest boiling point, and then also explain the reasoning. So we want to compare the different types of intermolecular forces we'll see there. And then with the bottom couple, we want to essentially just rank those in terms of the surface tension and the viscosity we would see in those different substances. But at the top, I just have the one that's highlighted. It's going to have the highest boiling point. And again, it's just going to be based on the difference in intermolecular forces. So the stronger the intermolecular force, the more that those molecules are going to be attracted to one another. So the more difficult they're going to be to separate. So if we think about boiling, going from a liquid to a gas, that's exactly what we're doing. We're just completely separating those molecules. We're essentially eliminating all intermolecular forces. That's why gases just expand to fill the entire volume of the container they're in. So with these ones, we want to identify in each of these pairs which is going to have the strongest intermolecular forces. So for the first one, we're looking at ethanol versus propanol, propane, excuse me. And with the ethanol, we've got that hydroxy group, so we've got OH. And then since the oxygen's bonded directly to that hydrogen, we're going to have hydrogen bonding here, which is going to be much more a much stronger interaction than the dispersion force we'll see in the nonpolar propane. So propane is just going to boil at a much lower temperature. And then with the next two, in this case, we're going to have very similar molecules in terms of their geometry, because each of them are going to have a central atom that's going to have a bond to each of the hydrogens, as well as two lone pairs. So it's going to be a tetrahedral molecular geometry, but with a bend shape to it. So each of these is going to be slightly polar. But with them, neither of them is going to be so polar like we'll see with the next one, where we actually have oxygen, and in the middle we're going to have hydrogen bonding there again. So that's why if we jump to C quick, that's why we see water is going to be a lot much higher boiling point than with the hydrogen sulfide, just because we're going to have the hydrogen bonding in that case. But with H2S versus H2SE, the sulfur versus the selenium, in this case, neither of them is going to be so electronegative that we're going to wind up with a superpolar molecule. So in this case, what we want to focus on is going to be the size of these two. And since selenium is going to be much bigger than the sulfur, we'll have more of that dispersion force. So we'll see the selenium compound is going to have a higher boiling point. And then with D, it's kind of the same idea. In each case, we're going to have a nonpolar substance. But with krypton, it's just that single atom, whereas bromine, we've got the diatomic molecule. So we're going to have two of those atoms. So it's going to be a bigger substance overall, so we'll just have more of the dispersion force there. With E, nitrogen oxide NO versus just diatomic nitrogen. So there's a couple ways we could think about this. Oxygen's bigger than nitrogen, so with NO, we'll just have a slightly larger molecule of a little bit more of that dispersion force. Or we can think about nitrogen and oxygen have different polarities, or different electronegativities, I should say. So that it's going to wind up with oxygen being slightly negative, nitrogen being slightly positive. So we'll have a little bit of a dipole in that substance, whereas N2 is going to be completely nonpolar. And then with the final one, lithium chloride is going to be ionic, since we've got a metal with a non-metal, but then the HCl is going to be just a covalent substance. So we'll see with the ionic compound is going to be a much, much higher boiling point. And then with the bottom question here, we've got methanol, ethane, and formaldehyde. And we want to rank them in terms of the surface tension as well as the viscosity. And what we're going to see is both of those properties are going to increase with a strengthening of the intermolecular forces. So since methanol here is going to be able to hydrogen bond, because we've got oxygen and hydrogen bonded together, just like we did up here with the ethanol, we're going to see that's going to have the highest surface tension. It's going to be the most viscous. And then formaldehyde, we still have oxygen, we still have hydrogen, but in this case, each of them is going to be bonded to that carbon. So we're just going to have dipole-dipole here. So this is going to be the middle of each of these. And then the ethane is going to have the least amount of surface tension. It's going to be the least viscous, just because it's going to have the least attraction to different molecules of itself. So if we just had pure ethane, there's not really going to be a ton of interaction between those different molecules. That would actually be a gas. Okay. So for these next ones, kind of similar, we want to determine if these molecules are going to be polar or non-polar based on the structures we're given. And then we want to look at the different intermolecular forces, so those different van der Waals forces, and identify which of those might be multiple, but which of those is going to be present in these different molecules. And then just at the bottom, you can see there we want to identify which of these substances would be the most soluble in water. But just looking at it quick, B is going to be the only non-polar one, just because we've got a chain of carbons with hydrogens on the outside. So none of those bonds are going to be very polar at all. Carbon and hydrogen are going to have very similar electronegativities, and then the carbon and carbon are going to be the exact same. So we'll see that butane is going to be non-polar. So we'll only have the London dispersion force. But we still have that London dispersion force in every substance. So even though the rest of these are going to be polar, we'll still have the dispersion force there. It's just the only difference is if it's just a regular polar molecule, it'll be dipole-dipole. But if we've got oxygen, fluorine, or nitrogen bonded directly to a hydrogen, then we'll have hydrogen bonding instead. So that's why with the remaining polar molecules here, in each case we've got hydrogen, in each case we've got oxygen. But because D is the only one that has oxygen bonded directly to a hydrogen, that's going to be the only one we have hydrogen bonding. The other two are just going to be dipole-dipole. So we'll still have a negative charge on that oxygen. It's just not going to be as negative as the oxygen at the bottom there. And then because of that hydrogen bonding, that's why we'll see this substance. So propanol, 1-propanol, is going to be the most soluble in water of these four options. All right, and then this graph here we want to use to answer these couple of questions related to vapor pressure. So with the first one, what is the approximate normal boiling point of the substance represented by curve B? So for this one, we just want to remember normal boiling point is just going to be the boiling point at standard pressure, so 1 atmosphere. This graph is in torr, so that's going to be 760 torr. But what we can do is just go at 760 torr, draw a line over to whatever substance we're interested in. So in this case, draw it over to B, and then just go down to whatever temperature that's at. And then you can see my line's not perfect just because the mouse is a little difficult. But we're going to have it at about 75 degrees Celsius. With a question like this, you don't have to get it exact. You just want to be somewhere in that ballpark. So if you had it a little closer to 70 or something like that, you'd still be correct. But we, of course, wouldn't want something like 80 or 65 or something like that. Which is something around 70, 75 degrees will be the normal boiling point for that substance. And then with the next one, which of these substances has the weakest intermolecular force? So with this one, we want to think about what vapor pressure is representing. And this is going to be the amount of pressure exerted by the gas of this substance that's above the pure liquid. So if we just had a container filled with A, a different one with B, and a different one with C, we're going to have some of that liquid. But the vapor pressure is going to be the pressure exerted by however much of that substance then goes into the gas phase. So with the weaker intermolecular forces, we're just going to see more of that substance is naturally going to make it into the gas phase. So we're going to have a higher pressure there. So the greater the vapor pressure, the weaker the intermolecular forces. So for this one, we want to look at the line that's furthest to the left, because at any given temperature, we can see that curve A is going to be higher than B or C. So we're going to have a greater amount of this substance. We're going to have a greater pressure there, meaning we're going to have weaker intermolecular forces. And then with which of these three substances is water, we want to think about the normal boiling point of water. So again, 1 atmosphere is 760 torr. We know that's going to be 100 degrees Celsius. So we would just want to go from 760 and just go over to which of these is then going to be lined up with 100 degrees C. And that'll just be substance C in this case. And then with the next one, which substance has the greatest vapor pressure at 40 degrees C? Kind of the same thing question 4 was asking. It's just going to be whichever one has the weakest intermolecular forces, whichever one's highest up on the curve, or on the diagram rather. and that's going to be substance A. And then with the final one, write a sentence describing vapor pressure and the strength of intermolecular forces in a molecule. Again, as the vapor pressure increases, intermolecular forces decreases, like we said with question 4, or we can state it in the reverse case, as the vapor pressure decreases, so as we're getting less of that substance into the gas phase, we're just seeing stronger intermolecular forces keeping it as a liquid. And that's why it's just going to take even more energy to then get into the gas phase. It's going to take an even higher boiling point. Right. And then in this one, we've got a phase diagram. So we've got all three of the phases showing the different lines representing the phase changes. And then we've got a series of different dots. We want to label what each of these represent. So with A, if we think about it, the states of matter is going solid, liquid, gas. So with A, we're going to see solid. If we skip ahead to G, that's just going to be the liquid. So just kind of going clockwise, we're having the phase changes there. And then with B, right in the middle where those three lines meet. So if you think about it, we've got three lines. That's going to be the triple point. So that's going to be the set of conditions in terms of temperature and pressure, where we'll actually see all three phases of this substance exist at once. C is going to be anywhere on this line. We would just consider the sublimation point, because that's going to be going directly from solid to gas. Just going across there. Or you could think of it as deposition, I guess, too, if you're going the opposite direction. So that was C. So D is going to be the critical point. Above that, in terms of temperature and pressure, we can no longer distinguish between liquid and gas, so it's known as a supercritical fluid. But D is just going to be the critical point. E is going to represent the melting point, or the freezing point if we're thinking about going left across that line rather than right. But that's just going to be the phase change from solid to liquid, depending on which direction we're going. F, similarly, is just going to be the boiling point, liquid to gas. So it could also be the condensation process as well. And then G, like we said, is just going to be the liquid in the middle. So if we had a point over here, this would just be the gas phase. So if you think about it, high temperature, low pressure. And then solids, low temperature, high pressure. So it makes sense that we've got the gases in the middle. And then if we look at this line, we're going to see a similar in slope to the one we see here. And we want to think about which of these substances, so we can see pretty much the only difference, we can see, of course, different measurements in terms of the temperature and pressure where these points are at, but the general shape is the same in terms of we've got kind of the curve here separating liquid and vapor, straight line between the solid and vapor underneath. But in one of them, we've got a slope like this, negative. The other one, we've got a slope positive between solid and liquid. We want to think about which of these is going to represent a substance that's denser as a liquid than it is a solid. And what we see is just the one on the left is going to be the substance that's more dense as a liquid than it is a solid. And what we can do is kind of just take a temperature where we start as a solid, and then just without changing the temperature, just move that point vertically. So increasing the pressure, and we'll see in this case, since we've got a negative slope, that means we're going to go from solid to liquid. And the only thing we're changing is pressure. So we're going to be forcing those molecules closer together. So we're going to see in this case, the liquid is going to be a little bit more dense than the solid. Whereas if we do it here and kind of just pick a point below this line and increase the pressure, now we're going from liquid to solid. So we'd see this one's more dense as a solid, and this is going to be the one that's much more common. This is going to be the situation we see with water, and that's going to be important in terms of life on Earth because it allows for ice to float on liquid water. So when we've got in the wintertime, like lakes and stuff, we wind up freezing the top of the water, the surface layer, before the bottom. That allows the ice to essentially serve as a protective barrier to the elements, helps keep some of the organisms in that system of water alive throughout the winter, because they're then protected from those more harsh conditions. But that wouldn't be the case, of course, if ice was more dense. It would sink. It would freeze from the bottom up in that case. So it just wouldn't offer that same protection. And then with these phases, we can also determine the amount of energy that's going to be involved in the transition from one phase to another, multiple phases, the heating or cooling just of a single phase of matter. And with it, we've got a couple different equations. We'll see with the slope sections of a heating curve, we've got very similar equations in the sense that it's going to be the mass times C. We can just see liquid and gas it changes to here, and a delta temperature. So with these ones, what we're looking at on the slope section is just how much energy it takes to heat or cool that phase of matter. So when we're looking at the C value, that's going to be our specific heat. That's going to be specific to the substance as well as the phase of matter. So that's why we're specifying gas, liquid, and solid will have a different specific heat. Even if it's all H2O, it's going to have a different specific heat for ice versus water versus steam. And then with the delta T, that's also going to be specific just to this phase. So if we have something that starts at -25 and then goes all the way to 125, that's not going to be the delta T for any of our calculations because we would just have -25 up to 0 for the ice one. We'd have 0 up to 100 for the water one, and then we would have 100 up to 25 for the steam one. So we'd have a different value for those temperatures for delta T for each of these phases because we're only going to be focused on each of these slanted sections individually. And then similarly with the flat sections, there we're not seeing a temperature change at all. So that's why we don't have the delta T in these equations here. But it still takes energy to melt or boil a substance. So once we get it to 100 degrees, it doesn't automatically just completely go from liquid to gas. When you're boiling water for pasta or something, it doesn't automatically just entirely disappear in just one split second. It takes a while to convert all of that water from liquid to a gas. And this is a similar process if we're melting something. And the same if we're cooling it, going in the opposite direction. But with these calculations, just note a lot of the times with the heat of fusion, heat of vaporization, instead of mass, so instead of M, a lot of the time we have moles, so N. And that means with our delta H values here, fusion and vaporization, just for the different processes, a lot of the times those values are going to be in terms of joules or kilojoules per mole rather than per gram. So we've just got to make sure that our units match up. So with the specific heat, for instance, it's often joules per gram degree C or joules per gram Kelvin, just because Kelvin and Celsius are going to be the same increment of change. They're just offset by 273. So that's why we have grams here, because we need to cancel the grams unit in the specific heat. But sometimes we'll have joules per mole here. So we've just got to make sure if that's the case that we plug in moles rather than the mass. But if we're looking at a heating curve question, essentially what we want to do is think about where on this curve we're starting, where we're finishing, and then for each section of this curve that we're on, we need to do one of these calculations. So if we started as a solid, went all the way to a gas, we'd have to do 5 separate calculations, like we see here. Or if we were just heating something from 20 degrees as a liquid to 70 degrees, then we would only need a single calculation. And then with this, just note as we're adding heat, so as we're heating something, it's going to be an input of energy. So we should have a positive Q value there. And then if we're cooling something, we're just going in the opposite direction. So there we'll have a negative Q value. But with this one, we're looking at water, and we're given the specific heats for the different phases, or even the heat of fusion, heat of vaporization. And then just note, in this case, everything's per gram. So we don't have the temperature factor in the heat of fusion or heat of vaporization, because those are just the flat sections. But we still just have grams for all of these, so we can just use the mass. We don't have to worry about the moles. But for this one, we're starting at -4, going up to 101 degrees Celsius. So in this case, we're starting as a solid going to a gas. So we're going to be starting just barely on this slope section and then going just barely to this slope section. So we're going to need 5 different calculations here. And with it, we kind of separated them out. So here we can see heating solid, then the solid to the liquid, heating the liquid, liquid to gas, and then just heating that gas, that final degree. So with this, just note with the delta T, it's always final minus initial. So that's why if we're going from -4 up to 0, 0 minus -4 still gives us a positive 4-degree change. And then a positive 100 here, positive 1 degree here, because in each case we're heating this substance. If we were cooling it, we would have just flipped these values. Then we'd get a negative delta T, and that would just make the entire term negative itself. But in this case, since we're heating it, everything's just going to be positive. But like I said earlier, since each of these either heats of vaporization or fusion in these cases, or the specific heats for the pure phases, they're all on a per gram basis. So we can just use 45.9. We could have really even pulled this term out in front and just had 45.9 times and then eliminated it from all of these. However you want to plug it in is totally up to you. But going through and plugging everything in, we should get 139,000 joules or 139 kilojoules. And then this one kind of did the same thing. In this case, we don't even really need this calculation, this conversion, because it's just asking for the amount of energy, and calories, excuse me, works just fine. So we could just keep it in these units if we wanted. But this is the same type of question, but this one's actually going to be a little bit easier because in this case, it's asking for how much energy does it take to take 10.5 grams of liquid ethanol at 68.4 degrees C and convert it to vapor at 78.4 degrees. But we can see 78.4 is just going to be the boiling point. So what we're doing is essentially starting on this straight line between C and D. So we're going to have to heat up that liquid a little bit, and then we'll completely convert all of it to the gas phase. But we're not going to start heating that gas phase at all. So we're only going to need 2 calculations in this case. How much energy does it take to heat that substance to the 10 degrees from 68.4 to 78.4? And then how much energy does it take to then vaporize all of that substance at that same temperature? So if we look at it, the first one here is just going to be the heating the liquid. So 78.4 is what we finished at minus the 68.4 that we start at. So it's a 10-degree change. And then with the second piece, now we're looking at just the phase change. So we don't have the temperature factor at all, just because it's going to be the flat section of the curve. And then when we take those two values and add them up, we're going to see where it's going to take 2,160. Oops, and actually that's incorrect because that's just going to be the calories. That would be 2.16 kilocalories or 2,160 calories itself.